All right, so we arrived last week at the Euler equations of a generalized extended energy functional, capital omega, where we also allow for the variation in the particle number. And then application of the Euler equation, so basically assuming a stationary equilibrium scenario where you can freely think about it like a thermostat containing a reservoir of particles, right? Like a particle reservoir, a particle thermostat. So instead of only exchanging heat, let's say, you also exchange particle numbers now. Then you have basically this omega is like the energy of the universe, and then in that universe you must have we impose this equilibrium condition resulting in the Euler equation, which allows us to identify our chemical potentials in complete analogy to thermodynamics as the derivatives of the energy with respect to variation of particle number. Right? And so last week we saw this once for the electrons, right? So that's this mu E here, right? And we gave the interpretation in terms of what we had previously discussed, also in terms of the Koopman's theorem and the ionization potential and electron affinity, etc. Just briefly rotate this so we have more space. Now, so this electronic chemical potential, this view on the frontier orbitals, right, and how they vary, this is very well established, and this is consistent also with the Aufbau principle by Hund, right, where you fill your levels, the lower levels first, right, and so if you add or remove electrons, you always do this at the frontier orbitals, right? That's where things happen, especially if you can assume that you are in the stationary equilibrium kind of scenario. Now, there are spectroscopical methods where you can shoot in electromagnetic waves at frequencies which correspond to the energies of the core levels, right? And then you can kick out core electrons. But that's obviously not an equilibrium process, and typically then your electrons quickly relax back and populate the lower states again, and leaving you at the end of the process with again with something like the ionization potential. Now, what is less common is the identification of a nuclear chemical potential, and also here we can have an Euler equation for the protons, and we arrive at the expression of the nuclear chemical potential, which we can identify as the electrostatic potential. So this was the integral of your electron density at R prime times an error function which switches off the electron density as you approach R prime, as you approach R. Typically there's some parameter describes the width of this this function. Now you could also use other functions to switch off your contribution, right? So this is somewhat an arbitrary choice. You need this as you consider the scenario that R approaches the nuclear position, right? So that will be this scenario. Then we call this the alchemical nuclear potential, and then it becomes clear that at this nuclear position, you do not need to get the repulsion from the protons. Oh, wait. I'm doing something bad here. This is an error. Wait. This is, of course, your proton charge distribution. Right? And then you have the electronic part here. Well, let's remove this. Yeah. Apologies. So you have the nuclear repulsion from the other nuclei, and you have the electron density, but you don't have the nuclear repulsion at the nucleus you're considering as you approach Ri. All right. So we have now a working definition, right? We have identified the meaning of these chemical potentials. And now what we would like to have, of course, is to make use of this in a unified general sense, right? And that is quite straightforward. If you recall your classical mechanics, there is a step as you go from Lagrange to Hamiltonian mechanics, and that is Legendre transform. So you can change your variables, right? You can switch from one variable to another by making use of the Legendre transform. So to write things in a generalized chemical potential, we want to use the Legendre transform. To switch from our extensive variables, which is number of particles, number of electrons or nuclear protons, okay? So our proton distribution, to intensive variables, which is the chemical potentials. Okay. So we can use the Legendre transform for this, and we use for this generalized chemical potential. Let's use. No, I'm doing something wrong. Wanted this. Okay. So we want as a chemical potential here, we want to use Q as a term. So our Q will become a functional of mu E and mu N. Right. Where again this kind of bracket denotes that we are talking about a functional. So if you feel not so much at ease with this notation, just think of functionals as integrals. Okay, an integral is a function of a function. So the most common functionals we deal with are integrals. Now this Q is. And now comes the Legendre transform, is your energy, which is a functional of your nuclear charge distribution and your number of electrons, minus, or let's make this even more explicit, of your electron density too. Now hang on. Did we? Oh, I'm sorry. We used now N for electron density. So let me just briefly rectify this. Here it should be N, right? So this is your conventional total potential energy. Okay. And now we use the Legendre transform. That means we can add or subtract a term where we have we sum up all those particle derivatives of where we take the energy derived with respect to these particle distributions times the particle distributions. Okay. So this is the Legendre transform, and thanks to Euler, we know that this, in short, is your mu E times N plus mu N times C. So this is the Legendre transform. So now our Q is a functional of this chemical potential, right? And so it's you can go back and forth between Q and E depending on what your variable should be. Now, this is all good, but then of course what really is of interest to us is then are the changes in the chemical potential. So changes in number of particles, changes in chemical potentials, right? What would that be? So what we really care about, as always, is the total differential. So for any process, right, whenever something happens, that means we have to write dq. Okay. Okay, what is dq? That is, first of all, dE. And then we have our the various contributions from all the variables that enter here. So Ne d mu E. Oh wait, so I forgot one step here above for the Legendre transform. Let me put it like this. This here is mu E, and this here is mu N. And now now you see that we have mu E times Ne minus dr mu N of R times C of R. Now, what happened here is that mu E is the global constant, right? It's not spatially dependent. And so you can pull it in front of the spatial integral, and then you integrate over the electron density and you get your number of electrons, right? So you have here, and these three terms are the energy, the product of number of electrons and electronic chemical potential, think HOMO or LUMO eigenvalue, and the integrated product of your nuclear chemical potential and your your proton charge distribution. So that's then why, as you go to the total differential, you first get this Ne d mu E minus mu E d Ne, and then the same for dr d of R mu N R plus E of R. Okay. Now, so we have these 5 terms, but the dE term is still implicit, right? So we can make that one, we can write out this total differential. Right? So this total differential, and this is a function of C and N, and the functional. This would be, we now have your prefactor here with E and E, plus dr dt dc dc of R. And so this is nothing else than your chemical potential times D and E. plus integral over mu n dz. And now you see already that because you have in the above line, you have negative signs, that some terms will cancel. So you arrive, you substitute this, you'll arrive at minus NE E mu E. The mu E dn cancel. This one cancels. And also this one and this one. So we're left with this expression. Now, the spatial integral over the nuclear charges, the proton charge distribution, can of course reasonably well be approximated by the sum over the nuclear charges with some delta function, right? So this would be this means your dq is something like minus NE changes in your chemical potentials, your electronic chemical, your changes in your HOMO, right? Scaled by your number of electrons which you have, minus the sum over all your nuclei and the nuclear charge at the nucleus, and the change in the alchemical nuclear potential at that point. Right?
Excuse me, quick question. You make this wiggly line, but this is exact, right? There's no approximation from second to last line.
Yes, there's the proton charge distribution is not a delta function. So the delta functions assume that you really have point charges, right? But in nature, that's not the case. Your cores also have your atomic charges have a wave function, right? The nuclear wave function. So it's even more general, right? So the equation above is still within Born-Oppenheimer, but it would still be consistent with a wave function ansatz for your nuclei.
Okay, got it. Makes sense.
That's how it's meant. That's a good point, yeah. So for all intents and purposes, for us, it's as good as numerically exact, right? But if you, so for instance, for protons, right, very light atoms where you have substantial nuclear quantum effects, this might be more approximate than for others. So the approximation is the nuclear wave functions approximated. It's point. Now, this is the result obtained in this, just for reference again, in the paper I wrote with Mark Tuckerman in the Journal of Chemical Physics, 2006 paper, right? Now, in the year 1982, a quite similar related result was obtained. So you can compare this to the following result, dq being written so again it's also here, it's an approximation, but dq is basically written also for the electronic degrees of freedom, but then rather than considering a reservoir for protons, right, as counterparts to the electrons, the authors have chosen to consider a reservoir of stoichiometries of chemical elements, right? Instead of having spatially distributed distinguishable nuclei, they considered your system is basically a bath where you can throw in any number of elements, right? And this stoichiometry then relaxes. And given that stoichiometry, so it's on the level above, on the first level we talk about. Right? While this, the grand-canonical ensemble as described in here, works for all levels. This result here only works for stoichiometries. The result looks like this. So alpha is your chemical type. The number of atoms of that type, and the change in some lambda parameter. So chemical element type, right? This lambda parameter would allow you to go from one type to another. So this was this samples stoichiometry only. So there's no spatial resolution for nuclei. And this was introduced by Capitani, Nalevaisky, and Bob Parr in the Journal of Chemical Physics in the year 1982. Yeah. Okay, now we have our total differential for this generalized Q, right? Now we have it expressed in terms of the chemical potential for electrons and protons. And now the next step is, of course, to insert our understanding about these properties. So let's write d mu e as, so we expand this in its variables, right? So mu e depends on z and n, right? And so we write d mu e with respect to number of electrons, right? So that would be the n derivative, right? So the functional derivative, we said that before already, for the electronic degrees of freedom results in a global number, which, as you might recall, is intuitively understandable if you think about your electronic wave function covering your system. The electrons are indistinguishable. And so if you insert an electron now from here or from here, there shouldn't be a difference in the energy response. Right? There's no spatial resolution in that sense, since it's one wave function, right? It's one object. Right? So this is why you really just have a partial derivative here, and then dNe. Okay. And then we do the same for d mu e with respect to nuclear charge. So now we have a spatial resolution, dc of r, and so we have to sum that up. Now, this is an interesting result. This is the second order derivative of the energy with respect to number of electrons, right? And as such, this is something like the curvature of your energy as a function of number of electrons. This is also called hardness, and we give it the symbol eta, the electronic hardness, aka electronic hardness. This prefactor here is also something interesting. It's the mixed second order derivative of the energy with respect to number of electrons and number of protons. And this is also known as the Fukui function. And here we call it molecular Fukui function R. There are multiple Fukui functions actually. So there's also Fukui function where you would vary the number of electrons and the atomic positions. Right? That would also be a Fukui function. So Fukui function is more general than this, but here it is the cleanest kind of Fukui function in the grand-canonical sense. Second order derivative, once with respect to electrons and once with respect to protons. Right? These are our elementary particles. All right, so we can, with these definitions, we can write it like this. All right. Now, we can, of course, do the same for our alchemical, or variation in the alchemical potential, right? So we have a d mu n of r, and that is, of course, also a function of your number of electrons and your number of protons. And so what you see here is in this first term. So again, this is a function of space. So we should have something like this plus, and now we we differentiate a second time, ER and what we now have is in this prefactor here, we have the derivative of E with respect to dz. But now this one gets derived again with respect to number of electrons, right? And so you see this is just in the other order, the second order mixed derivative, which we just discussed before. So if the order of differentiation doesn't matter, this is again our molecular Fukui function. And similarly here, you see that this is the second order derivative of the energy with respect to nuclear charge at R and at R prime. And so this is something like a nuclear hardness, okay, which must be some sort of kernel. To the best of my knowledge, this paper is the first one to discuss the nuclear hardness in the literature. Okay, so now we have all things ready, and we can combine everything into our grand. So we insert this. And we find for our generalized dq minus electronic hardness times Ne times dNe minus dr. And now we get the integral over our molecular hardness. But this shows up twice, right? In this part here. So we have it here, and we have it here. Okay. So this means as we now insert these terms here and here, we can actually factor out this molecular Fukui function. Right? So we have our molecular Fukui function here. And that thing multiplies our number of electrons. dz and our, to pay attention again, dz, and now I have dn, so Ne dNe.
That can't quite be right, but the mixed one with Z, right? Shouldn't like ZR DNE?
So Z, yes, it should be Z of R DNE. Okay, and then finally the hardness term is the integral over dr and dr prime, molecular hardness, nuclear hardness, r prime, times z of r times dz of r prime. All right, that was in terms of a global generalized expression that fully captures variations in our chemical composition on all levels of, on all the scales of chemical compound space. Are there any questions? So we should note, of course, the constraints, right? That as always, the number, so in terms of your Lagrange multipliers, we noted that above, right? You would have your number of electrons. And if you integrate also your nuclear charges, right, you recover the total number of protons, and the charge state then is the number of protons minus the number of electrons. That's just as a side remark. Yeah, and you also have at any the nuclear charge of atom I is, of course, the number of protons around of that atom, right? So you could write this as the delta function I C of R. That's the atomic number, nuclear charge. All right. So what we have done now is really within the common assumptions of quantum mechanics and electron density functional theory and the Born-Oppenheimer approximation, classical nuclear charge point charges, classical nuclear point charges, and so on and so forth. We have obtained the formal framework that allows us to consider variations in the elementary particle number to travel chemical compound space, right? And so this basically means that doing things like we discussed last week, right, where you go, you have this kind of scaffold here, right? Remember this, right? So you have scaffolds where you travel through this chemical compound space. All of that, right? Something like these interpolations here of different Hamiltonians that differ in nuclear charge distribution and different electronic charge distribution. All of that is possible now, right? And fully backed up by the entire framework of our quantum mechanical implementations. All right, I'd like to take a little break now. Let's resume at what is it, at 9:20, okay? All right, let's continue now. I'd like to switch gears a little bit and change now to slides. Let me share the corresponding slides. What we have accomplished so far is that we have laid the fundamental foundations, right, that connected the first principles view, which we discussed in the quantum chapter, to a chemical compound space. And what I'd like to do now in the remainder of this chapter is to discuss a couple of papers where these ideas were actually implemented and then have been used to generate numerical results. So what we can do for this are now, or what we can do now is to exploit alchemical transformations. And just to generally define this once more, so this is a common mathematical extension of our domestic models. So we extend the solution space for our Schrödinger equation to include cases which are not realistic. Right? There's no experimental counterpart or correspondence which you could possibly realize in this universe. And for that reason, we call it alchemical. Okay. Now, this might sound funny, but it's actually, as we discussed before, quite an old idea. So it's funny to those who see this for the first time, but computational alchemy is something quite well established. Now, one of the main goals is, of course, to then extract through inclusion of this extension, we can extract meaningful properties, typically through integration of state functions where the path does not matter. And so we can make predictions which then can be compared to experimental observations. So there's typical applications of this is that chemical compound space is sampled this way. So differences between different chemical compounds can be obtained. But you can also actually use this to accelerate sampling, because it means this basically extends the dimensionality of also our phase space, the configuration of space that is being sampled when you run molecular dynamics, for instance. And that is known also as alchemical free energy perturbation methods. So typical applications include thermodynamic cycles, this enhanced sampling, or compound design task as we are mostly focusing on in this course. Typical use cases include force field-based MD. This is actually, I think, in terms of, if you believe in democracy, right, if you just count how many people do it, then this is the most frequent use case in the field. Their entire conferences devoted to alchemical free energy calculations for in molecular dynamics, simulations for drug design, etc. In terms of quantum chemistry, so quantum alchemy is much less frequent. This field has been quite small for a long time, but it is growing. So this is quite encouraging. And then there's also the possibility actually to sort of combine these two and do something called path integral molecular dynamics, where you account, let's say, for kinetic isotope effects, and you can use alchemical changes also for something like that. Now, here's
maybe a silly question, but like, how do we come from the functional that we just derived earlier, or kind of what we've done before? How do we now come to better sampling techniques and rational design? Like, maybe I didn't quite get it, but I don't quite see how the one leads or improves the other.
So this will come now, right? That's,
okay, got it. Okay.
Exactly, yeah. So that's the point, right? So in the beginning, we had sort of the formal framework, and now we're going to discuss how to actually make use of it. That's the point. So let's start with this example here. You have on the left a molecule which is planar, right? The hydrogens are distinguishable to us, so we can index them, and you could so right now 3 and 2 are sort of an cis conformation, and you can imagine this change of the conformation from cis to trans, right, as you see it. So this would be a process which typically, now just substitute your hydrogens by differing residues, right, and then you break the symmetry, and then you'll see that these would be different conformers. Now, this kind of barrier is relatively high, so in ambient conditions, this is something that should survive. Yeah, and so just to illustrate how one can look at this, right, by through this extended worldview now of compound space, right? A traditional picture would be the one you see here. So you basically distort your hydrogen out of the plane, right? Here it stands out, and you push it over to the other side. So you do the torsional movement of your atoms in real space, and your energy will have to overcome this barrier, where basically you're sort of breaking the double bond, right? So you have to pay roughly, in terms of energy, the height is roughly the difference between the single and the double bond here in this example. So this would be the black curve, right? The ground state energy. And then if you sample this, a distribution would correspond roughly to this P, right? How the Boltzmann average distribution should roughly look like. Now, in this case, because all your substituents are the same, it's perfectly symmetric and degenerate. Right? So it's a very simple toy case. Now, it's already quite interesting if there's a common example actually for looking at excited states. You go to the first excited states, that's drawn here qualitatively as well in red. And if you excite your system, instead of overcoming this barrier, right, by kinetic energy or temperature, you excite your system, and it is allowed to access the excited state surface. Then you could also think you can promote your system here. It will relax to its minimum, actually being exactly where the barrier, the transition state is. And then it can go down again through loss, through dispersion of the corresponding energy in terms of, let's say, vibrations, right? So this is sort of first the ground state picture, then the excited state picture, and now you can add the alchemical picture, which would simply get you from one minimum directly to the other. If you wish, we tunnel through this barrier, right? We don't go through the pain of having to overcome this barrier. Rather, you start slowly scaling down the proton here on H3, while scaling up the proton where here we have this ghost hydrogen, right, which doesn't really exist. And that's where you know the location, and that's where you grow your proton. And in this case, for this change, your energy will vary much more smoothly. But of course, anything you do in between there is not physical, right? So anything that happens on this arrow here has no physical correspondence, no real correspondence. Only your starting and your endpoints do.
Wait a second, but you still have a barrier, right? I mean, like in the middle, you have something where you have half hydrogen on the left, half hydrogen on the right, and that is probably different energy than kind of initial and end state.
Yeah. It's not really clear what you would have. So yes, you should actually, you're right, you should have a barrier. And we will prove this later, right? The energy, the total electronic, the total potential energy. It's not necessarily a barrier. So you must have a barrier in the electronic energy, and this we will prove later. But it could be that because of the nuclei that this is countered. So we don't know a priori about the shape of this, right? And we will also see later that for certain changes you can exploit symmetry, and then you can make statements about the shape of the energy as a function of the interpolation. The important thing is for you to realize is to sort of extend your mind towards these new dimensions, right? They don't live in 3D. This is a new dimension that directly goes from one realistic minimum to the other one, but it does not live in reality. Right? There's no realistic correspondence. And that is, in my mind, that is maybe the most important concept in this course, right? That we can do this, right? That's what we've shown so far, right? That we can connect this to proper physics, and so we have the backing, if you wish, to allow us to exploit these things, and we can trust these results, right? So this is not just postulated or hypothesized, right? And that is also then when we go to the machine learning parts and we exploit similarity measures, right? They live in such extended spaces, right? And so this is consistent with our first principles view on quantum mechanics, on chemical compounds. All right, so what happens if you integrate then? Well, it's quite simple, right? The integral over the derivative has to be 0. So it has to look something like this. Now, is it something like a barrier where first you have to go up to overcome a maximum, or is it a minimum where first you go down to go through a minimum? We don't know a priori, right? But what is sure is it must be symmetric, so the integral over the thing will add up to 0 by symmetry. So we do have symmetries in compound space, right? And these are typically not exploited yet and strongly understudied. We don't know this yet. Just this year, we published a paper in my group where we discovered and presented a new symmetry in compound space, but there might be much more. There might be more relationships. This is just the first one that we found, right? And so to my mind, this is very exciting because there might be much more which we can discover, and maybe you'll be among those who will find new symmetries as well. All right, so let's get to some numerical results. This was a paper in 2007, and I believe it is the first one where approximate versions of Schrödinger's equation have been obtained, approximate solutions of Schrödinger's equation have been obtained for fractional nuclei connecting one compound to another. In particular, we looked at this case where you have a formic acid, right, on both cases, and it binds to a molecule, in this case methane, and we now transform continuously methane into ammonia. All right. So you can do this by annihilating this proton here. You scale down its nuclear charge while increasing the nuclear charge of carbon from 6 to 7, so that you have nitrogen. The total number of electrons is the same. Your total energy will change like crazy, right? You're changing chemical composition, you're changing stoichiometry. On the first level, right, you're changing the atomic, the energy of the elements, right? So you will have crazy changes in energy. But if you look at the relative energy of binding to this formic acid molecule, right, then you have a much more subtle change in energy. You're basically describing how the interaction energy with formic acid changes, right? Now, formic acid is just an arbitrary choice. It could be any other binding partner, but this is what really matters in chemistry, right? Typically some relative energy. In chemical applications or materials applications, we typically only care about relative energy. Nobody really cares about total energies for practical applications. But of course, our theory is much more general than just for relative properties, right? So we have, if you have a good picture, a good idea of total energies, then your relative energies are easy for you, right? It's close to trivial. So this idea, right, that this interaction energy is a state function, just like the enthalpy, right? Remember Hess law from thermodynamics, or simply energy conservation, right? That's the first law of thermodynamics. So any state function, the path does not matter, and as long as you integrate over it in a smooth and continuous fashion, right? So if you do a numerical integration, basically your grid size must be small enough, right? You will recover the same energy differences, right? No matter the path. And that's what you see here with this thermodynamic cycle. If you go from methane to carbon dioxide directly, or if you go through this gaseous water rather than the liquid water, if you have this intermediate state, if you sum up these energies, it's going to be the same. So here you see these, going back in time, these first changes in the electronic structure. What we have here, you see here on the right, the nuclear charge of the heavy atom, right? But of course, at the same time, the proton is scaled down correspondingly. So it's totally charge neutral, the whole complex. And you see this changing in steps of 0.2, 4, 6, 8. No. What is this? It's 2, 4, 6. Oh, I added 0.9 here. There's 1 point here. But if you ignore this one, this was just to check on the curvature here. But originally it's this upper one, right? In steps of 0.2, we change these nuclear charges, right? And for these steps, right, you see now for 0.2, 0.4, 0.6, 0.8, you see how the electron density difference due to binding That's what you're seeing here. How it changes as you interpolate these compounds, right? So on the left, you have the electron difference due to binding of methane. And on the right, you have the electron difference due to electron density difference due to binding on ammonia. And you even see here, so the resolution is quite bad here, but you even see here the hydrogen atom of methane, which does not exist anymore in ammonia, right? So this is just from the display software that it's still there, but it's not here anymore. There's no hydrogen, right? And so you see the electron densities, they actually moved inward, right? This is the lone pair electron of ammonia moving into this hydrogen bond, right? And you'd see also what happens to formic acid, right? Here, there are two hydrogens and they basically repel each other. So they push the electron away from the hydrogen bond. And now slowly, as you turn into ammonia, you have an electron build up here on the hydrogen atom, right? And that's of course, then here you have a hydrogen bond, right? And here you don't, here you just have some van der Waals interactions. So you would expect much stronger binding. And that's what you see here. The interaction energy for ammonia goes from something like minus 0.6 or so down to minus 20. Now there are two lines in this energy curve. The upper line corresponds to how the interaction energy changes if you do not move your nuclei. All atoms, the entire geometry is fixed, right? And you only change the nuclear charges, right? The lower curve shows what happens if you let the nuclei relax at each lambda step, right? And that also tells you, basically at each lambda step, a geometry relaxation was done here, right? And that shows you that you can relax geometries within for fractional nuclei, right? So in terms of quantum chemistry codes and implementations, there's no problem with fractional nuclei. You could even run molecular dynamics with it, doesn't matter. Okay, so remember we discussed protons and electrons, right? And so what does this mean if we start interpolating around here between some initial and some final Hamiltonian, where you can change your number of electrons or you change your nuclear charge distribution, right? So these are two independent variables, right? Whatever you do, they are independent. And if it doesn't really matter how you go from your initial to your final combination, right? As long as you do it continuously, right? So you could go in some arbitrary way, like shown in this red curve here, or you go by changing vertically only the number of electrons, keeping your stoichiometry fixed, and your geometry and your stoichiometry fixed, right? And then you're basically doing something like a redox process, right? That's redox chemistry, your varying number of electrons. So we discussed this with the Hemorrhage Theorem and so on. That's what you would be looking for. If you do horizontal changes for fixed number of electrons, then you can deal isoelectronically. So you can treat all constitutional isomers for given stoichiometry. Right? These are all, they only differ in Z. They have the same number of electrons. You can also change stoichiometry, of course, just like we changed methane to ammonia. So let's say hydrazine to methanol, right? So these are compositional isomers that are isoelectronic. Or you could also consider cases where you just have the same number of valence electrons, right? So you go basically going down the column in the periodic table, right? You could say, I only consider my valence electrons and I change my pseudopotentials that take care of the core electrons. And so then I can easily go from carbon to silicon. No problem. Right? So this is sort of the space in which the combinations which we should consider, right? What can we do in terms of initial and final Hamiltonian to sample chemical compound space. Now, if we want to look at how the energy changes, it means, of course, that we should be looking at derivatives. The number of electrons, as we discussed, if that is your variable, then things collapse towards your electronic chemical potential, and you would have your derivative discontinuities at integer number of electrons, right? And if you integrate over such changes, as you change number of electrons, you would get a free energy difference, and this would be the redox potential, right? So alchemy, in terms of number of electrons, allows you quote unquote easy access towards redox properties. So here's an example where I demonstrated this, and this was a numerical demonstration in this molecular grand-canonical ensemble paper, which we discussed earlier. We went to the redox half reaction of removing an electron from ammonia. Okay, so what does this mean? We reduce the number of electrons, right? If we integrate over this, we should get that free energy difference. So our integration limits should be number of electrons here going from 10 to 9. Okay. And what we have to integrate over now is the stat-mech average of the derivative of our energy with respect to our lambda, or the number of electrons here. And so this means we should sample the electronic chemical potential, or in other words, the HOMO eigenvalue as our charge is getting from neutral to +1. We're removing one electron. So how does this look like? So here you see molecular dynamics runs of ammonia molecules for different charge states, right? And so what is being monitored here, so as a function of time, what is being monitored here is the HOMO eigenvalue. So we're pulling out, we're decreasing the population number of the HOMO eigenvalue. So that's how you can do this in a quantum code. And at the same time, the charge increases, right? And so you see here, these diamonds correspond to the average HOMO eigenvalue, so the average here. And they indicate which charge you have at each. And you see a monotonic decay of your HOMO eigenvalue, right? Now, if the system was frozen, right, and we wouldn't let it equilibrate, the HOMO eigenvalue should be a constant, right? Remember, the energy should be a straight line, and the HOMO eigenvalue should be constant. But now we are talking here about a free energy difference, so we have to sample this, and so we can see how the HOMO eigenvalue is actually changing in a near linear fashion as you go from ammonia to ammonia plus, right? Now you do numerical integration over this, and you get an estimate of the free energy of the redox energy of ammonia. Just 2 years later, White-Tao Yang and co-workers used the same idea to calculate redox potentials in enzymes within QMMM calculations, right? In particular, they looked into the redox potential of an iron and a ruthenium enzyme. And here you see the paper, right? And so it's a fractional electron approach. You see here the sort of charge or population number, and here you see the average HOMO eigenvalue. So again, right, in terms of our worldview now on compound space, this is completely consistent, right? It's rarely done, right? But that doesn't mean it's not possible, or it doesn't even mean it's useless. It's just that it's unconventional. All right. Now let's consider some more horizontal changes, right? So so this is just to basically check the box. Yes, it's possible to vary number of electrons. But if we want to do this, there are actually many problems we inherit because of the approximate nature of how we typically solve Schrödinger's equation, right? And so this is actually not so easy. You can have you will have to go between different spin states. The approximations you're making might be more severe for one charge state than the other. And so it is, and also the number of electrons, as we said, it's at this 0th level, right? So it's really not for number of electrons that that chemical compound space explodes, right? So we could do all these things for fixed number of electrons separately, and that would be just one additional dimension. So if we vary now the nuclear charge distribution in an isoelectronic case, then we, as we discussed, we simply have the Hemorrhage theorem, which we can make use of, and if only the electron, if the electron number is the same, that means the two Hamiltonians are the same, and if we interpolate them linearly, they only differ in the external potential. So this difference here is the derivative of a linear interpolation of two isoelectronic Hamiltonians. And so all what you need here then is the wave function of the corresponding electronic state that gives you an electron density, and that gives you this derivative. Here is an example of this derivative. This comes from sort of a tutorial review paper from 2013. They also discussed the partitioning number thing. And what we see here is HCl being transformed into ammonia. Okay. So we are now really we are traveling across the periodic table in a diagonal fashion. Right? So ammonia is in the same row as fluorine, and fluorine is in the same column as chlorine. And in terms of valence electrons, you can simply interpolate them. In practice, in a plane wave code, you can interpolate the pseudopotentials in a continuous fashion. And you do this linearly, and then you can also generate the derivatives. So the energy change, this is actually the deprotonation energy. So the protonation energy. So you add a proton to the system, and you look how the energy difference looks like as a function of lambda. And this protonation energy you see here as a square changing from HCl to ammonia. So ammonia is a base, right? It attracts protons, and HCl is an acid. It wants to release its proton. So this corresponds exactly to what you would expect in terms of chemical intuition, right? Now, how does the derivative look like? What you see here is two derivatives. This is what you see here. Once you can simply fit these squares and differentiate that fit. And then you would get this dashed line, or you calculate the derivative from Hellman-Feynman at every point. And then you get this these diamonds. And so this is basically a validation that this Hellman-Feynman theorem for your pseudopotentials does, roughly speaking, what you would like it to do. Here's another example. We can change H2 into helium, right? Isoelectronically. So you take the two protons, and one proton gets annihilated, the other one is being turned into helium. And so you can change the energy this way. This is some unpublished numerical results. Chris Anderson, who's a math professor, he implemented an exact version of the Schrödinger equation, which you cannot use for many electrons, but of course for just 2 electrons in a small basis, it's very much possible. So now we come to this question of what happens in between, right? So Michael asked this question, right? And it's a very good point, right? It's also discussed in the paper reference below. But the proof we are going to consider is was not presented first in this paper, right? This was, you will find references then pointing you towards the original proof. It's actually quite a simple proof, right? Once you go through it, once you work it out, it's quite obvious that it has to be this way. But basically for the electronic path, the electronic energy, you can show that whatever you do, the energy must be concave. Okay? So it means it should always go up. Now we are talking about the absolute electronic energy. Okay? Mind you, if you look at relative energies, things might be very different. Right? Now, this still doesn't mean it's irrelevant. Imagine, for instance, you're looking at energy differences between constitutional isomers. All constitutional isomers have the same reference state for their atomization energy. It's always the free atoms that they are composed of. So if you compare constitutional isomers in their total energy, that's the same as comparing constitutional isomers in their atomization energy. So this proof is quite powerful. Right? The statement is quite powerful, but you have to be careful that you don't mix it up with the wrong properties or that you consider it in the right context. All right, let's go for this. For a discussion of this, and then we probably have to have another break. So you consider 2 different isoelectronic paths, right? Connecting some initial to some final energy through some order parameter lambda. And first, you consider the energy where you linearly interpolate the electronic Hamiltonians. Okay. So typically the energy is then nonlinear. So we call this E nonlinear. Right? E nonlinear is the expectation value of the linear interpolation of the Hamiltonian, as you see it. Right? Now this is the QM average. You can pull out the initial Hamiltonian. And you have to evaluate this as a function of lambda, right? So it's with the wave function changing of lambda, but it's always the energy of the initial die. And then you write the expectation values of the other 2 terms like this. So this is the energy of the initial system with the wave function or the electron density at some lambda value. And then you also have lambda times the energy of the final system for the wave function at lambda, and again the initial. And now you consider some unknown interpolation. We don't know how the Hamiltonian is being interpolated, but it will be interpolated such that your energy is linear in lambda. Right? So that's basically the straight line, getting you from initial to final. Right, with a straight line. And what we're going to show now is that the linear interpolation of the Hamiltonian will always be above the linear one, will never be below. Okay? So we know that the linear energy in lambda trivially must be must look just like this. Okay. So this is what I just said. We're going to show this now, that the nonlinear energy is always going to be above the linear energy. So you can insert equation 2 in equation and equation 3 in the hypothesis, right? So we just write this here again, and so now we insert the equation 2. We put it in here, and you rearrange things, right? So there's some things canceling, but what you find in the end is that your initial energy at lambda minus your initial energy is in this bracket. That will be this difference, right? And your final energy at lambda minus your final energy will be in this bracket. So we have these two terms, and each term is a product, right? The question is if the sum of these two terms is then larger or equal to 0. And this is the case because lambda is between 0 and 1, right? So this bracket here will be larger than 0. And also here, this lambda is larger than 0. Right? So we have two positive prefactors here. They will not make this whole thing negative. And then we have to consider these two brackets, right? And what you have here is the energy. This is the expectation value with some trial function at lambda. This is not the optimal wave function, right? So this will, by variational theorem, this term will always be larger than EI. And similarly in this brackets, right? This term will always be larger than EF by variational theory. And hence all the four brackets, all the four terms which we have here, they are all positive. The whole thing must be larger equal to 0. So it's a simple proof based on the variational theory. All right. So let's maybe take a little break again, and let's reconvene at maybe 10:15. Okay.
Excuse me, quick question.
Sure. One sec.
Sorry, I had a quick question. More auxiliary thing. You said you're gonna continue the lecture at 10:15.
Yeah.
I have another lecture, unfortunately, at 10:15. But you said you do a recording somewhere and
Yes.
upload it somewhere. Okay, perfect.
Yes, it's this thing called YouTube.
Already heard of it once before, I think.
Yeah, please subscribe.
Okay, then thanks for the lecture and see you next week.
Yeah. All right, let's still continue. So we just showed that your electronic energy must be above the linear line, right? And so this implies really that you can expect your electronic energy to always be concave. Okay, so it's always of this shape, right? And you can see this easily by saying, okay, you interpolate only a small. The proof works for any change in lambda, right? So if you don't believe it for a big change, right, you can always go to a smaller one and make that linear interpolation, and it will always be above, right? So that means if you're always above arbitrary linear segments, means you must be fully concave, right? So this means that any second order derivative must be negative. Okay. So let's continue now. We would like to discuss now the case of not only electronic changes, but also compositional changes and the corresponding free energy changes. Right? So if we assume this, this linear kind of Hamiltonian here, then we can get the derivative as the expectation value of the Hamiltonian difference. And then by virtue of chemical thermodynamic integration, we now have here the energy S in your Boltzmann factors, which corresponds to this thing. Right? And for thermodynamic integration, for this partition function and this free energy integration, so this is StatMech 101, you then see if you enter this free energy derivative, this means you need to differentiate this thing. So you get the 1 over q from the logarithm, and you have to differentiate q with respect to lambda, and your lambda sits in the Boltzmann factor of your energy. So you differentiate that once more, and then you see this is nothing else than a Boltzmann weighted derivative of the energy. And so that derivative is our QM derivative in here. So you have the StatMech average of your QM average, which you have to integrate over lambda here, right? So 3 integrals, right? The StatMech integral, the quantum integral, and the lambda integral. They will give you the free energy difference between any compound on this in this universe. So I'm pretty pumped about that, right? I think this should be in every high school textbook, but of course it's not. All right, if you do this not only in quantum but just in a force field, so presume you have some analytical form of your quantum energy, some potential, then you can interpolate these potentials, right? And that would be your quantum derivative. And then you can evaluate the StatMech average and the lambda integral. And this is not uncommon in, as I said before, in molecular dynamics applications. So 2 scientists who contributed or are still contributing to a large extent on this are Ed McGinn at University of Notre Dame and Wilfried van Gunstern at ETH Zurich, who recently retired. Now, a typical example would be something like shown here on the right. So imagine you have you have a bunch of polymers in a periodic boundary condition setting, and you run molecular dynamics, they vibrate and wiggle, and then you ask this question, okay, what is the chemical potential for inserting or removing one of them? Okay. And so you could, of course, try this with Monte Carlo, right? So imagine this blue one just gets inserted with at random coordinates with a Monte Carlo move. Now, the likelihood for you to get a Monte Carlo move that is accepted, meaning that none of the atoms of your polymer clashes with any of the pre-existing atoms, this likelihood is extremely low. So in practice, grand-canonical Monte Carlo for entire molecules really never works. It never converges, right? And so it is here that these alchemical changes are incredibly useful, because they allow you to first insert just one atom, then you alchemically grow the second, then the third, then the fourth, and you grow your polymer like this. You integrate over this change to get your free energy difference. Everything can be done in smooth fashion, and you will very rapidly converge towards meaningful free energies of insertion. Another example is the problem of melting. Okay? So if you have never thought about melting, it's from the simulation point of view a really intriguing and fascinating problem. Now, there are multiple ways how to tackle melting. Okay, so one way is depicted here. Right? So you can build a unit cell of your material where you include the two phases, the liquid phase and the solid phase. And this comes from this paper by Yu Cheng, Xanteas and JCP 2009. Right? So you have two phases and you see the boundary, right? If you monitor something like radial distribution functions of each atom, right, then you can easily detect which atoms are at the boundary. Right? Their radial distribution function will change from sort of discrete peaks in the crystal towards smooth functions in the liquid. Now you can monitor where in your box these boundary atoms are while you're running molecular dynamics, and you can vary the temperature of your MD, right? And if your temperature is too high of the MD, your boundary will start melting the crystal. If the temperature is too low in your MD, your boundary will start crystallizing the liquid, right? So the boundary will move depending on your temperature. Now, the temperature at which the boundary does not move, that's your melting point. Right? That's when the two phases are in equilibrium. Right? By definition, it means the free energies of the two phases is the same. So that's the temperature at which your system would melt. Now, just imagine doing this. You need a huge box to get things converged, right? You also need the crystal structure, right, of the solid phase, which is not an obvious thing. You don't necessarily have that, right? And if you take the wrong crystal structure, you might get the melting point for the wrong states of aggregation, right? So that's not a helpful thing, right? So this is not an elegant and efficient way of getting the melting points. It's a possible way, it's a feasible way, right? But you can, if you think about it, you will realize that it's really something quite demanding, right? So typically, to get a good melting point is nearly an entire research paper just for one material, right? To predict it. You should also keep in mind, actually, that melting points can be measured and are being measured. And It could even be much simpler for you if the compound is available to just go and measure it. If of course only if in the phase diagram you're interested in conditions that are easily accessible for you. So this is this option basically, right? Another option would be to say, okay, let's start with the crystal in a big cell. We just run MD and we slowly increase the temperature. And at some point, the crystal structure will break down and compounds will start diffusing, right? And that's also something you can easily detect with some simple analytical functions like the radial distribution functions. You can detect when that happens. But there's a problem with this, right? You have severe finite size effects, right? If your unit cell is too small, right, you impose too strong of a periodic order, you will have a dramatic effect on the onset of melting with the temperature. But even if your box is very large, which means much more expensive, right? Even if your box is very large, you will also have problems because actually, depending on how quickly you increase the temperature, the melting point will go lower and lower, the slower you increase your temperature, right? So basically, the more expensive your simulation, the more accurate your melting point. So there are some hysteresis effects, and you can do this at multiple ramping speeds of your temperature, and then you can extrapolate back to zero ramping speed for your temperature, right? And that's what you would guesstimate. But that's an extrapolation, right? And the predictive power of your extrapolation depends strongly on how well converged your results are. And so this is also a very cumbersome way of predicting melting points. Now, in both cases, the one where you actually simulate the boundary and the one where you simulate the process of melting, in both cases, you need to know the crystal structure. This is not obvious, right? For any new compound, it's very difficult to predict the crystal structure. There are crystal structure blind tests taking place regularly, where people try to predict crystal structures for new compounds. And this is a major challenge in the field, right? So just to get a decent crystal structure guess might already require you to do an entire PhD if your compound is non-trivial. So this is one of these cases where you might wonder, can alchemy actually be of help, right? And so here's a paper published by Sai Jayaraman and Ed McGinn in the Journal of Chemical Physics in 2007. This was part of the PhD thesis of Sai, where an alchemical thermodynamic cycle is used. Now, the way they did this was to take a molecular liquid, and you have a force field that describes it, and you weaken the interactions between the molecules, right? So then you have a weak fluid. Then you condense the box towards the size of the crystal. Typically, crystals are more condensed, right? Unless it's water or so. So you make the box smaller, you shrink it, right? And so you have the dense, weak fluid. And then you presume some crystal lattice, and on each molecule, you put a weak biasing potential towards a certain lattice site. Right? And so the molecules will be attracted. It's a spurious fake potential that attracts the molecule to a certain lattice site, but it can still rotate as much as it wishes, right? So it will align in something that would be an ordered weak phase, right? And then you switch back on the intermolecular interactions. So then you have the strongly ordered condensed phase, and that would be your crystal estimate. Now, so you see now, we are doing something like alchemy, right? We are going into interaction regions which have nothing to do with reality. Right? Weakly interacting molecules, what is that supposed to be, right? So this is not something you could ever measure experimentally. But what you can do is integrate the free energy derivatives along these paths. Along each path, going from one state to the next. Right? Now, if the free energy difference between your liquid and your crystal is zero, right? This energy difference, if it's zero, then the entire integral must be zero, right? Because it's a thermodynamic cycle. And so what they did was to calculate this free energy difference over the cycle at different temperatures for running molecular dynamics. You basically run at different temperatures. You do this the entire cycle at different temperatures, and you look for the temperature at which the integral over the cycle sums up to zero, and then you know that's the temperature where the free energy difference is the same, and so that's the melting point. Okay. So when I saw this, I thought this is a really neat example of how powerful alchemical changes can be, right? You didn't need to know about the crystal structure. This converges very nicely. You can already think how to scan best this temperature ranges and so on. You can think about adding other states, intermediate states, to make it smoother, to make it faster, right? All these things you can do. In any case, you don't need to simulate the entire boundary, right? You don't need a giant box. You don't need to study hysteresis effects of temperatures and melting crystals, which you don't know. So this is a very compelling paper, I would say.
So, how many cycles did they need to perform? I mean, basically how many temperatures did they need to like sample?
I forgot what you'd have to look this up, what exactly they did. Of course, your result also depends then on the quality of the force fields, right? So it's a bit tricky, but you can imagine you first do a coarse scan, right? And then you do sort of divide and conquer, you know, okay, it's in between these two guys, and then you do a coarse scan, then you always go, you can rapidly zoom in there, right? And you also know by comparison to similar molecules where roughly you would expect these melting points to be. So it's not, in practice, I think it's very efficient, right? You don't have to run many cycles, I think, to get decent estimates of the melting point.
Okay.
So when I was at Sandia National Lab, I hired then Sai to join me as a postdoc, and we worked on using these kind of ideas for a problem which is already related to materials design. Right? I'm bringing this up in this part of the course already because there's no machine learning, right? So it's just an example of pure alchemy being already helpful for materials design. The application we were looking at were these so-called concentrating solar power facilities. So you can think of, there's one in Seville in Spain, this is the one in Sandia in New Mexico, but there are others in California and Arizona, and also in North Africa. People are building up these facilities, and they are quite appealing, actually. So the working principle is very simple. You have a tower which on the top of it has some container which contains a fluid, okay? And the tower is surrounded by mirrors which can orient according to the position of the sun, and they will all reflect the sunlight onto this one container, right? So you get very high temperatures up here. actually you get much higher temperatures already for modest facilities. You get temperatures that are higher than you need to. Right? This means that there's still room for exploiting this much more than we currently do. So you could store much more heat than we currently do. But anyhow, so in here there's a heat transfer fluid. So basically it's a fluid which you can heat up with the sunlight, and then you store the hot liquid in a separate container. Now storing hot material is something quite energy efficient. Just think of your thermal coffee mug or coffee can, right? Just by including some vacuum or including some even just air as an insulator, you can keep the heat for quite a long time before it is fully dissipated. So this is an elegant way to store energy, actually, quite efficient. And then whenever you want to make use of the energy, you use the hot fluid to evaporate water and generate steam, which you can then use to run a turbine to generate electricity. Right? And in this process, the hot liquid cools down, and this cold salt, this cold fluid can be returned then to the molten salt. Now, the question that is related then to materials design is what should be this heat transfer fluid? Which material should this be? Now, there is a simple relationship which you might recall from Thermodynamics 101. It's Carnot's efficiency of a heat engine, right? Carnot's efficiency of a heat engine is directly proportional to the temperature interval which you can cover. Right? So the larger the temperature difference between your hot and your cold reservoir, the higher the efficiency. Okay. In other words, the larger the temperature range in which your heat transfer fluid is liquid, the higher the efficiency, the lower your kilowatt hour price, okay, in the production of energy. So directly proportional, right? I very much like this materials design example. It's one of these cases where as you go through chemical compound space, if you manage to optimize the temperature range in which you have a liquid aggregation state, you will directly have an impact on the economic viability of such facilities. Now, so typical temperatures here, and this is again another cartoon of the same idea. So the sun heats this up, and here you see something like 560 degrees Celsius in terms of hot, and cold is something like 300 degrees of Celsius. Now, you need obviously, so you can easily reach 1,000 degrees and more in terms of of heating, okay? The problem is then that most heat transfer fluids, they consist of small molecules, and they will start decomposing if you heat them too much, right? And then they will escape, they will evaporate and be corrosive and destroy your pipes and everything. So you don't really want that. You want some heat transfer fluid that is heated not too much, right? So before it gets too hot, you will start using it and you will pipe it in the hot salt reservoir. Now, what about the cold temperature though, right? So 280 degrees seems sort of high, right? Ambient conditions are much lower, right? You're something like, yeah, I don't know, in the desert it can get cold, right? So you would want this stuff not to freeze, but you could go, yeah, down to, I don't know, 10 degrees maybe, right? So there's still a lot of room as you consider your 300 degrees Celsius. So advanced heat transfer fluids would have a temperature range in which they are liquid. So more than 500 is difficult if they are nitrate-based, which is commonly a common thing. But to get this below 100, right, towards 20 or less degrees Celsius, this would be really desirable. Now, if you use a traditional salt without nitrates, let's say some sodium chloride or something, right? They would start solidifying quite at rather low temperatures. Already at 150 degrees Celsius. You could, of course, use just some oil, but these oils would decompose, right? So ideally, you would have a liquid which goes from 0 or less up to 500. Right? That would be the best. Now, in this study, we focused on nitrate-based compounds, and the reason was that at the time of our work, there was a patent by some colleagues I had at Sandia National Labs, which had this composition. So sodium, potassium, lithium, and calcium nitrates in these ratios. Okay. They would, this was the best possible heat transfer fluid on the market in these 4 components. Right? So you had basically a 4-dimensional optimization problem with these 4 guys. Now, at the time we were working on this, a new patent was proposed going up to 7 components by these guys, Rade and Badowitz. You can look it up in the Journal of Solar Engineering. And they used a robot to scan the different temperatures. The different mixtures, right? Now, just imagine you're doing this. This goes back to the introductory part of our course. This is Edisonian research, right? Edisonian search. They did this experimentally by trial and error. You try one combination after. So, of course, you do it in a smart way, right? You don't really try all combinations, but you sort of try to zoom in. But still, you do this one after the other. And for each combination, you have to make the measurement. Because as I just said, to calculate a melting point, it takes a PhD just for one combination. So it's faster to do it experimentally, and they had a robot to do it, and they went up to 7 dimensions, right? So you have here a ternary phase diagram. The color is the 4th dimension, then you have ion 5, 6, and 7. Right? So this is a 7-dimensional problem here. Sometimes people say humans cannot think more than 3 dimensions. I think I don't know where this myth comes from. It's ridiculous. Here you're easily grasping a 7-dimensional problem, I believe. All right. So we wanted to look at this in terms of alchemy, right? What could alchemy do for this? And the problem of finding the lowest melting point is identifying the eutectic, right? So the eutectic mixture, if you have a mixture of 2 components, the eutectic mixture is that mole fraction where your melting point is the lowest in your phase diagram, right? And so what we did was to consider a mixture of atoms A and B, or molecules A and B, right? So suppose you have some mole fraction here. Then you can turn one of the molecules B into a molecule A by alchemy, right? And you can ask yourself, how does my free energy change as I do that, right? And this change, if you have a big box with many molecules, if you do it just for one of them, it's like a derivative, right? That's the change of your energy with respect to removing one molecule B and inserting a molecule A. So that's something like a chemical potential of mu AB. And so we can turn on and off the force fields of molecule A and B, and we can get this free energy difference by integrating over this change. Of course, we have to run MD for every lambda value along this change, right? And so this is what we get then. here you see the free energy changes, so this delta mu AB, as a function of mole fraction as you go from lithium nitrate to potassium. There's a potassium lithium nitrate mixture. So we go from 0 lithium nitrate to 1 lithium nitrate, and you get the free energy changes as a function of this mole fraction. So we ran molecular dynamics here. Here, wherever you have a blue dot, we ran long molecular dynamics for this lambda integration. So every dot here is a lambda integration. Right? And this is this curved line. This is what you get for the liquid. And here for this blue dot, you see such a lambda integration. This is how it looks like. So this is the StatMech average as a function of lambda, and you do a numerical integration. So the surface over this thing is what you see here as a blue number here. That's what's shown on this axis. So you see this blue line, but then there's also a red line and a green line. And their difference is that they correspond to different sampling temperatures. Here you see the temperatures for each color, right? So we go from 400 Kelvin to 423 Kelvin to 450 Kelvin as you go from blue to red to blue to green. Now that's the free energy of the liquid mixture. We approximate the free energy of the solid by a linear estimate of the free energies of the pure elemental solids, which are relatively easy to approximate. And so you put these at different temperatures, you put these linear interpolations, and the temperature at which they touch, right, where you have the tangent, that's the lowest liquid free energy being the same as the solid. So that's the lowest possible melting point. That is your eutectic. So that's what you see here. That's the blue, this blue line. So we did more scans. They are not shown in this figure, but here you see the blue dot. That's the lowest, the melting point is 423 Kelvin. And the mixture, the eutectic mixture, is the position where they touch. So by theory, we estimated it's something like 0.59 mole fraction, right? Turns out experimentally, it's 0.55. Right? Experimentally, the eutectic melting point is 410 Kelvin. Now you see a deviation in melting point prediction of 13 Kelvin. You might think that that is a lot, but actually this is an extremely good prediction. Typical predictions of melting points by atomistic simulation, if they are on the order of 30 Kelvin, they are good predictions. Okay, so this is an exceptionally good prediction. It's only 13 Kelvin deviation. Now, of course, we can do this also for sodium, potassium, and lithium. Then you have the ternary phase diagram. And on every binary diagonal, right, you can repeat this game, changing A into B while keeping the C at that current level constant. And then you can map out the predictions shown here in blue, right? So at the borders here, you have the pure binary sodium lithium. Here you have the pure binary potassium lithium. Here you have the pure binary sodium potassium. And we can also go in between, and we can even, due to the StatMech sampling, the MD sampling, we can even include some uncertainties here, which are shown in blue. But you see basically the eutectic for every combination of binaries, and the ternary prediction of the eutectic is here with 411 Kelvin. There are some experimental numbers, and they are shown here. These are experiments. Okay. And you see it looks similar, it's not identical, but it looks similar, and also the scale of the energies of the temperatures looks similar. So this is an illustration how you can use alchemy, for example, to rapidly identify in compound space combinations of stoichiometry, which are helpful for a very obvious application in terms of materials for energy application. Now I'd like to bring up one other example where molecular dynamics was used. This is actually Venetian molecular dynamics. I just showed this one slide. It's sort of an overview, but the application is completely different. Right? So I show this to illustrate the incredible versatility of these alchemical changes. This is a Nature paper by Dario Alfe, Mike Gillen, and Price, where they did alchemical changes of compounds which I expected, or of compositions which I expected to be present in the Earth's core. Okay? We don't know the chemical composition of the Earth's core. Nobody ever went there to measure it, obviously. So it's an open challenge, right? And we would like to infer it. And one way to do it is, of course, to make use of the planetary motion, right? So we have certain mass and momentum constraints which you can use. And if you impose those during your ab initio MD, allowing for variable composition, right? So it's like a thermostat on your composition to modulate the mass. And I think they also included the magnetic field. You can actually converge towards the most likely chemical composition that would be consistent with all these constraints, right? And of course, with the energy, you're also assuming that energy is being minimized, the free energy, right? And so with such an approach, alchemical ab initio MD, using DFT, so this was ab initio MD, they could actually converge towards reasonable suggestions for the chemical composition, the most likely chemical composition of the Earth. Okay, I have one more example. Yes, I have one more example of classical MD. This is the insertion of a proton in a liquid, okay, in water, actually. You can, of course, try to model this with molecular dynamics, where you take your ion and you pull it out of the liquid. Right? So this would mean you'd have to study the boundary and pull out the ion into the gas phase. This would be a terrible idea to study such a process. Would require immense computational resources, a huge simulation box, thousands of atoms. The convergence of this thing is going to be terrible. You will have to run this many times. And so what seems to be much more elegant would be to alchemically insert a particle and to integrate over this path, right? And this is what you see here. We inserted a lithium ion. We grew a lithium ion in liquid water. You see here for different lambda values. We started out with a noble gas without charge, and then we slowly switched on the charge. I believe it was helium. We basically placed the helium there, and we slowly grew the charge. And you see here the electron density averages at every lambda value, and the electron density gets attracted towards this charge. So there's electron density built up at the charge, and at lambda equals 1, you have the full the ion fully inserted. And we can, of course, calculate the StatMech averages at each lambda value and integrate it like this. And this is what you see here, this average, and this. So you have to look at get the free energy difference. You have to integrate these curves. And so we obtained with DFT and force fields very similarly looking curves. And if you integrate them, we get free energies of hydration ranging from -126 to -128 with a density functional theory. With force fields, you'd have something like 134.9. And in the experiment, people are debating. The experimental numbers range from -130 to -137. So what you see is here, this alchemical calculation gives you numbers which look very reasonable. It's very efficient, very, once you wrap this, your mind around this, right, it's very obvious that this should be much smoother and faster to converge than modeling the actual process, trying to model the actual process as you would observe it in experiment. Okay, with this, I'd like to conclude for today. And if there are any questions, please ask them now. Otherwise, we stop now, and I still wish you a good end of the week.
Thanks. Bye.
Bye-bye.
Thank you. Bye.
Thanks. See you next week.
Bye.
Bye.